Hi, my name is Professor Dave Goldberg in the Department of Physics. I am an astrophysicist and a theoretical cosmologist, but I am also the author of several pop science books, and my most recent, The Universe in the Rearview Mirror, got me very excited about some recent events in particle physics that you may have read about in the news, and I thought I'd spend a little time today telling you about one of the biggest, and that is the discovery of the Higgs boson. My title is What's the Matter with the Higgs Boson, which is a little bit of a play on words, because if you know one thing about why the Higgs was supposed to be such a big deal, it's that the Higgs is supposed to give mass to all these particles, which, if you didn't know any better, might seem kind of ridiculous. After all, we're used to mass being just a thing that is. Mass, as you may or may not remember fondly from your days at Drexel, is a property that basically tells you how difficult something is to move. But when the Higgs was first discovered back in 2012, uh, it was all over the news and it was a little bit overhyped. So people would say, finding the God particle, or the key to the universe. And by the way, that quote there, the elusive particle seen as key to the universe, that's a headline from the New York Times. So people got very, very excited about this, but there was a sense in which they sort of overplayed it, because one of the biggest problems with the Higgs is that it's difficult to sort of explain how it works in human terms. Now, the Higgs was such a big discovery that almost immediately it was awarded that the discoverers were the people who originally theorized it were given the Nobel Prize in 2013. The Higgs is responsible, as they say, for the origin of the mass of subatomic particles. But even for physicists, the Higgs can seem a little bit obscure, a little bit difficult to describe, which is why we tend to give these really flawed analogies, including things like the God particle, to newspapers. So what I'm going to try to do today is give you a sense of how it is the Higgs really works, give you something that you can take to your next cocktail party, that hopefully you can then dazzle everybody with your knowledge of particle physics. So the one basic concept of what mass is comes from Newton's famous equation, F equals ma. In other words, mass tells you how difficult something is to move. The greater the mass, the more difficult it is to get moving in the first place, and the more difficult it is to stop it once it's got going. So what does that mean? It means that all things being equal, massive particles are going to move a lot more slowly than low mass particles. So one of the analogies you'll hear in the newspaper, and I've seen this in the New York Times and elsewhere, is that the Higgs is something like the Higgs, what's called the Higgs field, which permeates the entire universe, is very much like molasses. And the idea with molasses or some other very viscous fluid is that you drop something in it and it goes very, very, very slowly through the material. This is really actually kind of a terrible analogy, because it imagines that the universe is sort of permeated with some fluid, and as we move through the fluid, we're going to be slowed down. But the problem is, if you something that starts off moving quickly, as it goes through this fluid, is going to go slower and slower and slower and slower. But Newton's first law of motion says objects in motion stay in motion, objects at rest stay at rest. And so as a result of that, the idea is, well, the Higgs field doesn't slow things down that are already moving, it just makes them more difficult to move in the first place. So this is kind of a bad analogy. And there's been a whole cottage industry of trying to explain using some metaphor how the Higgs really works. Now, let me just give you one other example to make things clear. This one actually won an award from the UK Ministry of Education. The idea was that the Higgs is like a celebrity at a party, or actually guests at a party, and a celebrity walks in, and the crowd all gathers around her, making her motion very, very difficult. And just like with massive particles, because the motion becomes more difficult, that's like mass. It becomes difficult to move. Of course, it doesn't explain why some things get more mass than others, why some particles are less massive when some particles are more massive. We have a whole particle zoo, and some are extremely massive particles, like these things called the protons and neutrons that ultimately make up our atoms. Some are lighter, electrons, and there are some that have almost no mass at all, things called neutrinos. Um, it doesn't explain why there are still completely massless particles, like the particles of light called photons. So what I'd like to do is take a little bit of a step back and sort of give you a bird's eye view of what we know about physics, how particle physics really works to a physicist. And basically, this is just this enormous triumph of of human understanding. So there's this thing called the standard model of particle physics that divides all of the forces in the universe into four different categories. One, at the very bottom of the list, is gravity. Gravity is described by a totally different theory, Einstein's theory of general relativity, and it's completely separate from all of this. But the other three, the strong force, electromagnetism, and the weak force, describe how atoms are held together, how individual protons and neutrons are held together. They describe how the sun is powered. They describe just about everything you could think of. And they all work in sort of a similar fashion. You've got one particle, say an electron, which is something you're probably familiar with, and another electron, for example, and they repel one another. And they repel each other using electromagnetic force. But what they're really doing, the way we really understand it, is they're sending a little signal back and forth to one another using an intermediate particle called a photon. That's the particle we call light. And they send those signals back and forth, back and forth, back and forth. And every one of these forces works in this way, and the properties of the mediating particle tell you how the force works. Now, the amazing thing about the Standard Model is we've basically predicted from it all the particles that should exist in the universe, and we've now with the Higgs, found every single one of them. But the Higgs basically was introduced to sort of answer sort of a nagging question about how all of these things fit together. So if you go through and sort of work through the mathematics of the Standard Model of physics, you find that all of these mediating particles, all of the things that do in the communication, should move at the speed of light. Now, there's only one type of thing that moves at the speed of light. Nothing can travel faster than the speed of light, but the only things that can travel at the speed of light are totally massless particles. Photons are massless. But there are these particles called the W and Z bosons, the things that mediate the weak force. And the weak force, by the way, very, very important. It's what's going on inside the sun that fuses the hydrogen into helium and ultimately produces all of the radiation that comes out of the sun, that powers our plants, that heats the air, that allows life to be possible here on Earth. So the weak force is ridiculously important. But, as the name would suggest, it's also incredibly weak. And I'll give you an example. Many particles interact in more than one way. So electrons interact with the weak force, but they also interact electrically, which means that they're very easy for us to find. That we've known about them for more than a century. We can produce them very, very easily just by heating up a piece of hot metal and detect them just by sending them through an electric field. This is how old televisions worked. But some forces, so the weak force is so weak that it produces a type of particle called a neutrino that only interacts with the weak force. And just to put this in perspective, a neutrino basically can travel through a light year's worth of lead and basically have about a 50-50 chance of interacting with anything. So these things are incredibly weak. Very, very, very difficult to detect. What you're seeing in this image is Super Kamiokande neutrino detector. It's this giant underground cave. And basically, just so you put it in perspective, the sun produces as many neutrinos in a day as photons, as ordinary light. And yet, even so, this detector, this giant detector, detects about half a dozen neutrinos a day. Almost not at all. So what that means, the reason the force is so weak, is that the mediating particle, the W's and Z's, are just incredibly high mass. It's like throwing one of those those medicine balls in the gym, right? They're very, very massive. They can't throw them very far, and thus they're very, very, very localized, and the force becomes incredibly weak. Where does all that mass come from? Well, the most famous equation in physics, E equals mc squared, can be rewritten. M equals E over c squared. If you create an energetic interaction, that creates mass. And indeed, I'm going to give away a little bit of the secret here. Most of your mass, for you as a human, comes from just the energies of interactions of particles. It's really quite remarkable. We think of energy as being this sort of ephemeral thing, and yet it gives rise to what we think of as permanent, which is mass. So to really understand where the Higgs comes into all this, you need to understand fields. And the idea is that we're permeated with what's known as the Higgs field and many other fields, electromagnetism and so on. These are just waves sort of propagating through space. And the idea is that we perceive these flows of fields, as a flow of particles. That still seems a little bit too complicated because I'm describing everything moving in this three-dimensional space. So instead, think of something much simpler, like a musical instrument. This is my daughter's ukulele. And the idea is that in a one-dimensional universe, the pluck of a string basically tells you about sort of the flow of particles. And the higher the pitch, the greater the energy. So the idea is that these might represent the energies of all sorts of individual particles. Now you can describe how hard a string is to pluck by imagining sketching the amount of work that it takes to go from one side to the other. A low mass particle flows very, very easily from side to side. A high mass, you have to put a great deal of force in from side to side. And so mathematically what happened in the universe was there was a field, and as the universe got cooler and cooler and cooler, that field settled down into a configuration where it became very, very difficult to budge. In other words, where you pluck it and it hits a very, very high pitch. That's the same thing as saying the minimum amount of energy you could put into it is very high, or in other words, that it has a great deal of mass. That is the Higgs field itself. So what does the Higgs field do? And that's where the Higgs itself got mass. But what does the Higgs field do? The Higgs is like the CAPO. All of these particles have a certain amount of energy, and the Higgs field comes along, and lo and behold, not a great chord, I admit, but it raises the energy, it raises the frequency of all of the particles that are interacting in the universe. And as such, raises their overall mass, and again, produces something like the W and Z particles with a great deal of mass, and therefore makes the weak force weak. And that was the central mystery. And so when the particle was actually discovered at the Large Hadron Collider, this was an incredibly big deal. Here's this very, very massive particle, roughly 130 or 140 times the mass of a proton. Very, very massive particle. And two different experiments, Atlas and CMS, sort of discovered it more or less independently. And it was one of these discoveries that was just of the first order of historical importance. Because number one, it explained this huge mystery, and number two, it completed our picture of the standard model of particle physics. As I mentioned earlier, they were the theorists. Higgs was one of them, and there were about 5 other theorists who came up with the idea around simultaneously. Were awarded the 2013 Nobel Prize. Englert and Higgs shared it, but there were several others, I think, who got sort of robbed. And the Atlas and CMS experiments themselves didn't get the Nobel, but perhaps they deserved it as well. But given that there were several thousand investigators involved in those experiments, it seemed unlikely that they were going to split the Nobel several thousand ways. So I wanted to leave you with one other thought about the Higgs, which is it's gotten this reputation in the press. People typically call it the God particle, which I think is a terrible name. First of all, it makes you sound like a crazy person. But I think most importantly, it's because it doesn't explain all of the mass in the universe. People have this idea that it explains all of the mass in the universe. It doesn't. So for example, your protons are made of more fundamental particles called quarks. And those quarks, yes, get their mass from the Higgs. But It turns out when you take all of the mass of the quarks in your protons and your neutrons and add it all up, it adds to 1 to 2% of the total. And all of the rest of it is the energies, the huge energies of interaction of these quarks flying around and interacting with one another. So literally 98% of your mass has nothing to do with the Higgs. Your atoms would almost be completely unchanged if the Higgs never existed. But your molecules would, because electrons without mass would just fly right off, and you couldn't do any chemistry at all. So as a physicist, that bothers me a little bit, but our chemists, I think, would be deeply, deeply bothered by that. So thank you for listening. Thank you for joining this presentation. I have a big social media presence. I hope you'll send me any questions you have about the universe or about the Drexel Physics program. You can find me on Twitter at Ask a Physicist, my email, goldberg@drexel.edu, and I blog at User's Guide to the Universe.